In this video, we'll use L'Hopital's rule to evaluate a limit, including two arctangent functions, arctangent of 2x over arctangent of 4x, and we're going to look at what happens as x approaches 0. It's probably a good idea to begin by reviewing what the graph of arctangent looks like, and in this case I've drawn the blue curve is the arctangent function here, and we can see it passes through the origin, so arctangent of 0 is equal to 0. As x goes to infinity, it approaches pi over 2, and as x goes to minus infinity, it approaches minus pi over 2. We can try to directly evaluate this limit at x equal to 0 to see what the form of the expression is, and in fact we get arctangent of 0 up top and below, and so I'll get 0 over 0. I put it in quotes because this is an indeterminate form. It really has no meaning as I've written it. What we're saying is the numerator and denominator are approaching 0, they're getting close to 0, and we're interested in that ratio. It's far from clear what happens to that ratio without knowing how rapidly these functions approach 0. And luckily, L'Hopital's rule helps us calculate that answer. In this case, I'm seeing 0 over 0, so L'Hopital's rule applies, and I should take the limit, and I should compare the derivatives of these two functions. I'll take the derivative of the numerator and the derivative of the denominator. Let's just quickly review what the derivative of the arctangent function is. Derivative of arctangent of x is 1 over 1 plus x squared. I'm going to be applying it in each case with the chain rule. So when I do the numerator, the derivative is 1 over 1 plus the input to my function, which in this case is 2x squared. I'm going to put 2x in there, and then I need to use the chain rule and multiply by the derivative of that input, 2x. I then do the same thing for the denominator. Again, the form of the derivative is 1 over 1 plus whatever is going into the function getting squared. In this case, it's going to be 4x. And then we need to multiply by the derivative of 4x. And L'Hopital's rule guarantees us that this limit is equal to our original limit. So let's finish the calculation. The denominator has 2x squared. So I'm going to see 4x squared when I'm done squaring both quantities, and I'm going to multiply by the derivative of 2x, which is a 2. Similar expression down below, I'll now get 16x squared from squaring 4x, and the derivative of 4x is 4. This expression now can be obtained by directly evaluating at x equal to 0. In fact, this function here in this new limit is continuous at x equal to 0. If I just plug in everywhere I see x, I'll have 1 over 1 plus 0. That's a sensible expression. 1 over 1 plus 0, again, a sensible expression. And if I simplify, I get 2/4 or 1/2. So my original limit is equal to 1 over 2. For comparison, let's just compute a couple of other limits related to the same function. Let's look at what happens as x goes to infinity. And I'm going to look at the arctangent of 2x as x gets large. So that's really the same as looking in my original graph here. As the input to the function gets large, be it x or 2 times x, as I move out this way, the graph will approach pi over 2. And a similar limit for the denominator, as x approaches infinity, arctangent of 4x will still approach pi over 2 as well. So their ratio is in fact approaching 1. As x approaches now minus infinity of the same function, the denominator and numerator will both approach minus pi over 2. We're looking in the other direction here. And therefore the ratio, because they're both negative, will be 1 as well. And so a graph of this function would look something like the following. As x approaches its extremes, we're seeing it get closer and closer to y equal to 1 in both directions. And as x approaches 0, we saw that the value of the function approaches 1/2. Notice that the function is not defined at x equal to 0, so I've put a little hole in the graph here, but what we're seeing is a removable discontinuity at x equal to 0. I could easily plug that hole in by putting in the value to be 1/2, and I would remove that discontinuity. I would have a continuous function now, and so those three limits are all exhibited in this curve that I'm seeing here.